So it's a great pleasure to have with us again Guilfoyle, who will tell us about the smooth Poincare conjecture in 4 dimensions.
Thank you very much. So I'm going to talk about the smooth Poincare conjecture in dimension 4. I'll try and put a little bit of a historical context. And I think the good thing about these conjectures, I mean, maybe it's a bad thing, it can be quite easy to understand, but then the difficulty lays in trying to actually kind of get something to work with. However, what it does mean is that to a general maths audience, actually, these are quite understandable in some sense. So let me see what exactly I'm talking about. So let me just state, there's different versions, you can do it in different categories. I guess we might call these so generalized Poincare conjectures. And I'm only going to look at 2 versions, I guess, because there's other categories you can work in. So the first one states that any closed n-dimensional topological manifold is homotopy equivalent homeomorphic to the standard to S. Okay, so that you can go from homotopy equivalence to homeomorphism, that's one version of it. Now, these are beyond what Poincare originally conjectured. In fact, it's an interesting story behind that. But in any event, so the other second one is that any closed n-dimensional.
Sorry, you mean Sn, the sphere, right?
Sn, sorry. Yeah, n sphere. Standard n sphere. So n-dimensional. So again, let's just say smooth manifold that is homeomorphic to to the n sphere is diffeomorphic. To the standard. So in one case you say something that looks homotopy equivalent to the n sphere, you say, well, therefore it must be homeomorphic to the n sphere, or if you start out with being homeomorphic to the n sphere, then in fact it's diffeomorphic to the n sphere. Okay, so these are, again, there's other versions you could replace homeomorphism, say, by PL, by piecewise linear. There's different various degrees of subtlety, etc. around that. Now, I'm going to talk about the stages of this. I mean, all except one are proven. This is disproven, for example. So I'll explain exactly what's true and where they come from. But to do that, let me just be completely clear. I'm not going to use an awful lot of heavy machinery, but we definitely need to know exactly what we mean by homotopy equivalent, and we definitely need to know what we mean by homeomorphic, at least. So let's just start out with some basic definitions. So the first one is we start out with a topological manifold. So again, when I talk about a topological space, it's always assumed to standard that it's separable and Hausdorff, for example, these are equivalent names that you could describe, you could use to restrict certain types of pathologies. Moreover, to say that it's a manifold, so that implies that it's locally, well, homeomorphic to Rn. So that, about each point there exists a neighbourhood where it looks homeomorphically bijectively. So when I say homeomorphism here, just to be clear, again, by homeomorphism, of course, we have a topology, so I'm talking about a continuous bijection with a continuous inverse. So this is throughout. And so this would be a topological manifold, would be n-manifold is separable Hausdorff topological space, which is locally homeomorphic through these homeomorphisms with a piece of order at each point. Okay, and then what do we mean by smooth? Well, we'll talk about smooth manifolds as well. So instead of being locally homeomorphic, you might want it to be a little bit more than just continuous maps. You might want them to be smooth. So you have a tangent space and all our usual calculus. So this is just a topological manifold, and by a smooth manifold, we mean all of the above. So equals all of this, except we add that these are diffeomorphics. So locally, and you can patch them together by smooth manifolds. Local diffeomorphisms, and they patch together to give you a smooth atlas on your manifold. So these are topological manifolds and smooth manifolds. So this is the class of objects that we're dealing with. Okay, so that's fairly standard. What about homotopy equivalence? So here we just have to do a slight step back, and let's talk about what we mean by homotopy equivalence. So homotopy, so first of all, let's just start if you've got two maps, F and G, and they map a manifold, n-manifold to itself. So these are homotopy equivalent, or homotopic, I guess is the usual way, or homotopic, if there exists a continuous map F from n cross 0, 1 to n, so I squeeze it in there corner, continuous, so that, let's see the way I wrote it, F of any point 0 is F at that point, and F at point 1 is G. Okay, so you can deform one map to the other just by a continuous family of maps between the two spaces. Okay, that's one thing. And now we want to say what do we mean by, as we have up here, what do we mean by homotopy equivalent for manifolds? So M1 and M2, so these are two manifolds, are homotopy equivalent. So this is the key thing in the first statement up there. So what do we mean by that? So essentially you have two maps, so there exist two maps. You have F, say, goes from M1 to M2, G goes from M2 back to M1, and maybe as a matter of notation up here, if two things are homotopic, maybe we'll just put a twiddle between them. Standard is an equivalence relation, and you can, so this is our notation. Just this tilde will be homotopy equivalence. So what do we mean for these two to be homotopy equivalent is that F after G is homotopic to the identity on M2, and G after F is homotopy equivalent to the identity on M1. So you don't require that they be, that they cancel each other out, that they be inverses, but at least they be homotopically, they look like they're inverse to each other. You can deform them until. Now, this is a weaker notion. It takes a while to kind of unravel the definition, but you find that this is quite a weak notion. So this is reasonably weak. And in what sense? Well, if you don't make any restrictions on M1 and M2, you can kind of find things that are homotopy equivalent that aren't even the same dimension. So for example, if you take the annulus, that's homotopy equivalent to a circle. Just a deformation retract, right? So you can write down these maps explicitly and you can see exactly what they are. But you can see that F and G being homotopy equivalent, they don't even have to be the same dimension if you don't put any more restrictions on the M1 and M2. Alright, so the annulus, this is a particular type of homotopy, it's homotopy equivalent to S1. Okay, so yeah.
What is a closed topological manifold?
Okay, so without boundary, I mean compact with no boundary. That's all. Okay, so it's quite a weak notion. It's certainly, they don't even have to be the same dimension. Now, if you don't have a boundary, maybe it's more restrictive, so they might be quite so good if you don't have a boundary. But for example, if you take, or n, or the 4-ball, it's homotopic to a point. Homotopy equivalent to a point. So such manifolds are called contractible manifolds. Contractible where you have the same homotopy type as Rn. contractible. All the homotopic groups are essentially trivial for such an example. Now, just to help me again, just to make life a little bit easier later, I have this one single twiddle means homotopy equivalence. Obviously, it's a lot less than homeomorphism. Obviously, it's weaker. So, again, just to make an introduction, small piece of notation, I'm not going to use it, I'm not going to have it very much, but we have, we'll write, for example, M1, M2 for homotopy equivalence, in the same way as I did for maps equivalent. And if they're homeomorphic, let's put 2 equals. So this will be homeomorphic. So this means continuous bijection with continuous inverse between 2 spaces. And then finally, if we have smooth, let's put 3. So that's when it's diffeomorphic. There's a diffeomorphism. Okay?
Yeah. So this is not even just locally homomorphic.
Yeah. I'm just going to use those for closed manifolds anyway, so yeah. Okay, and let's also introduce the following terminology now. I want to point out this terminology was introduced many decades ago where the words didn't mean the same thing as they do now, but let's take, so suppose you have some standard manifold, n-manifold, n0, right? Then M, another manifold is a fake version of it if they're homotopy equivalent but not homeomorphic. So, M0, not. Okay. So this is what you would call something that's fake. It's got the same homotopy type, but it's not the same homeomorphic because they're not the same as topological spaces with regard to homeomorphism. And then we also have M is exotic. This is another standard issue in this context. If it has the right homeomorphism type, in other words, it's homeomorphic to your standard model, and it's not diffeomorphic. So it's not diffeomorphic. So you have fake things which are homotopic but not homeomorphic, and then you have exotic things, putatively, possibly, again, which are have the same homeomorphism, are homeomorphic to the underlying manifold, and but they don't have they're not diffeomorphic. Okay, so that's all the terminology really that we'll need for the rest of the talk. But let's now come back to these generalized Poincare conjecture. So let's rephrase them now in terms of what we have here. So the first conjecture would state that there does not exist a fake Sn, and the second would mean there does not exist an exotic Sn. So that's essentially just using the words that we put up there to restate those 2 generalized conjectures. Now, as written there, they're not all true, and let me explain now what the current status is of such a conjecture if we were to put them like that. Okay, so let's talk about Sn. So this is the Poincare conjecture. I'm going to talk about different dimensions, and we're going to try and fit in what's known what isn't. So first of all, suppose you want homotopy to homeomorphism. Right? So this would be number 1 to homeo, and here you have homeo to diffeo. Again, all just for Sn. Okay, so for dimensions n less than or equal to 3, the 2 conjectures are both true. Right? They're both true. The final piece of this is, of course, Freedman. There's proof using Ricci flow. Right? So that was the final piece of it. It involves a lot of other people before that, etc. For dimension 3, this was specifically in dimension 3. It's also true in lower dimensions. Going from homeomorphism to diffeomorphism, so So I think that's related to, I think, Moise, I think is the name again. These are in the 50s. There's a lot of about triangulations of manifolds, and here you use PL structures instead of diffeomorphism, but it's the same thing in low dimensions, and high dimensions are different. So okay, it's a complicated story, but essentially it's true in 3 dimensions. All of that complexity somehow gets taken away. And then you have in the 60s a big explosion of results for n greater than or equal to 5. And here, again, for n greater than or equal to 5, it's true in this category. And the names associated with it are, of course, Smale, Stallings, Zeeman. So for all dimensions greater than or equal to 5, is proved. Now, one of the reasons why it's greater than or equal to 5 happens to work is because the methods that use embedded disks and embedded disks in 5 dimensions, while a generic disk in 2-dimensional object in 3 dimensions will have no self-intersections. But once you get into lower dimension, then you have problems. So anyway, they proved it. For all dimensions higher, it's true. It's not true for n greater than or equal to 7. This one here. It is true here. And I think actually the same names are associated with the proof in dimension less than 7. But for n greater than or equal to 7, this was already known, so these are the famous Milnor spheres. So for example, Milnor showed that S7, so this is not true. So this conjecture is not true. There are exotic differentiable structures on 7 manifolds. 7 sphere and higher, right? And higher, the dimension gets bigger, the more you get. What's interesting is it's defined at 28 differential structures. So they're homeomorphic to S7, but they're not diffeomorphic to S7. They have different differential structures, yeah?
Is that connected to the fact that in high enough dimension there starts to be this distinction between having a smooth structure and being just a topological manifold?
Yes, and as I could also put in PL. PL becomes distinct again from both smooth and topological. So there are, yes, exactly what happens. I mean, in some ways, you have enough space. If you think about it, how do you give a differential structure? It means you attach a tangent space, right? And this is what Milnor did. He gave a weak notion of a tangent space, and then showed that when you looked at the 7 spheres by certain topological constructions, which were plumbings on spheres, he could construct things that did not have the same. The tangent space was attached in a different way, so they end up with different differential structures. But this is why it's discrete. There's only 28 because it's a topological construction when you have enough space in higher dimensions for the boundary of the manifold to pick up some interesting, differential structures other than standard.
So is it, Milnor did it then for dimension 7 conjugate to 8?
A 7 and 8 and 9, so that you can look at Sn, and so the number goes. Yeah, and so you can. And what's more is, I should say, that you could take one of these S7s and you can connect it to another 7 manifold and give it an exotic differential structure. So you could put these together with others, so it proliferates exotic structure, but finite number. You go up to higher dimensions, 256, 200, 700, then it drops down to 2 in another dimension. But it's all through homotopy groups of spheres. It kind of looks like homotopy groups of spheres. It's that kind of strange, there's no periodic element to it, there's no kind of pattern, and at least the pattern is so deep it's hard to see. But in every dimension higher, you do have an exotic differential structure. So on S7, and you do have, you can make other manifolds that are exotic, that look like one that you know, but actually have a different differential structure. But there are a discrete number. Okay, now we come to dimension 4. So here we're exactly between the methods, right? This is kind of falls through the cracks in dimension 4 because these methods don't work because disks lower down because disks are no longer embedded. A generic disk has self-intersection. If it's immersed, it'll be immersed rather than embedded. And so the proof here, so the conjecture was proved, and I'll be talking a lot about this in a minute. Freedman 82, I think the paper came out, to prove the topological 4-dimensional Poincare conjecture, and then this is our question. Okay, so that's the whole. That's the whole I want to try and explore a little bit around. Why is it that this one little piece is left out of this picture? Okay, by the way, personally I believe both of them are true. Both conjectures are true, so you know that the 4-dimensional Poincare conjecture, both topological and smooth categories are true. But if you ask most mathematicians who work in the area, they'd say there's a good chance that the smooth Poincare won't be true. And I'm going to explain why that is. There's some doubt over to why this is true, why this could be true. And this comes down to this. So my main point is that the reason, if we want to answer simply the question, why is the smooth four-dimensional Poincare conjecture still open? And the reason is because no one understands this proof. Now, what's more, not only does no one understand this proof, it's highly likely to be incorrect. And because of that, it has sown confusion throughout dimension 4 and caused basically all the wrong questions to be asked. So that's what I'm going to talk about. And I'll have to come back. Now, as I say, I believe that conjecture is true. I don't believe this, but the proof is incorrect for the following reasons. Okay, so let me come back to this dimension 4. So what we're looking at is, how do you prove, how was the four-dimensional topological one proven in 82? Okay, so actually I might start with the new board. This is somehow the key to an awful lot of comes and arrows. So what I'm going to write up is a famous disk theorem, which essentially has a byproduct which proves the Poincare conjecture in topological category, but unfortunately or unfortunately it leads to a whole lot of other things that suggest there's something else going on here. Okay, so this is the proof of the Poincare conjecture, topological four-dimensional. It's what's, I'm going to just refer to it as the disk theorem. Now it originates Andrew Casson in 73, and then was essentially the main component in Freedman's proof in 81, 82. Okay, so again, I'll just put in some basic ideas just to give you a flavour. So let M be simply connected. Just all cancel right. So topological four-manifold, and Fi is finite collections of disks. In fact, I want this manifold to have a boundary. I'll draw a little picture in a second, you can get a picture. So I want it to be a proper map, so that the interior of the disk goes to the four-manifold. This is a four-manifold, and I said that just a bit. Okay, we got a four sub, and into the boundary. So this is a collection of disks. They're only needed to be immersed, so they can have self-intersection. And there's actually a few conditions. They're homological conditions that are slightly technical, but the important one, I guess, is that if you take Fi and Fj and intersect them, you get algebraically. So here you have two manifolds intersecting in a four-manifold, and these two manifolds generically going to intersect in points, and you can give them a sign depending on whether they agree or disagree with the orientation of the manifold. You can give them an index, you can add them all up. This is what you get, right? This is the intersection number of the two disks in the four-manifold because of the dimension. We want them to be zero, so this will be their algebraic intersection is zero. Right? So they might intersect, but maybe the plus and the minus cancel somewhere, so you end up with zero overall, what we call an algebraic intersection. There is also another condition on homology. I won't go into it, it doesn't really play a role, it's not particularly difficult, but it's something that's used to kind of calibrate things. So there's one extra little homological condition as well. And under those two circumstances, with those two assumptions, I think that's all we need. Yes, let me just double check. I guess, sorry, there is other thing. I suppose you want the circles to be disjoint to the boundary. So here you have your manifold M. I suppose it's the inside here somewhere. Here's M. Here's the boundary of M. And then you have these disks. Now the disks might self-intersect. They might intersect each other. But they start and end with the boundary. So cutting down everything by dimension 1, that's by half the dimension. Each of these is the disk, and it might have a self-intersection, and they intersect each other. Here, for example, plus and a minus intersection, so that's okay. And the conclusion is that there exists these open sets, and we can take relatively open sets in M, such that disjoint So for each one of these disks, you have these disjoint sets. Let me draw them and you get a better idea of what we're talking about. They're essentially start and end. So essentially you kind of somehow can pull the disks apart and pull them into this part here. And this one, you could say pull apart. So that'll be V1, that'll be V2 or something. But notice we've separated them. So what we're actually doing is we're trying to pull these two apart. So they're algebraically not intersecting because they're intersection 0, but we actually want them geometrically separated, absolutely separated from each other. Okay, so we're going to do that. What Casson proved by various arguments to show that this here with the following property, that each one is homotopy equivalent to a two-disk crossover. So it's homotopy. These are Casson handles. These are often referred to as Casson handles because of this. So, if you like, it comes to a kind of constructive technique in topology where you take a given manifold, you attach other handles to it, and these handles can be of various dimensions. This is the type of, R2, so it's D2 cross R2. It looks like this. They're disjoint. And if each intersection with the boundary is an open neighborhood of the neighborhood of F the boundary is the bed. So you have your this is S0 it looks like because we cut a dimension, but it's actually an S1 and these intersect on an open, right? So somehow you're just containing the whole of the complexity given by these disks just in these two areas, these two bands. These have the right homotopy type to be handles, to be two handles, they have the right homotopy type, and the claim from the 81 paper can be all boiled down, so this is 82. So according to Freedman, so this is the 82 paper, VI are homeomorphic to two disks, to these two handles, open two handles. So this is the big claim, the fact that you can go from homotopy to homeomorphism in this here. Okay, so that was, I guess, the history is a little bit strange of this paper. This result was a kind of an attempt by Casson to try and get to, well, he didn't really get that, he got to homotopy and then he kind of stopped, and it was a lecture notes that he'd given in the 70s, and then later in the 70s, Freedman took them and then said, oh no, in fact these, so actually when these came out, it wasn't until 1986 that the actual lecture notes for the original result in the homotopy result actually were published, but they were going around, the notes were going around at that point. Okay, but what you can see is this is very, very general, because this is saying that if you have some kind of homological condition here, you're now getting rid of the self-intersections and just replacing them by a disk with the normal neighborhood. Right? If it's a homeomorphic too, then you have a disk and then you have a normal neighborhood to it. Right? So you have a nice disk. You have separated anything that was algebraically not connected is now geometrically not connected and intersect. If you had self-intersections, you managed to magic away the self-intersections. All the self-intersections gone. So this is an extremely strong result, and it goes way, way beyond the Poincare conjecture or anything like this. This has a big impact on four-manifold topology. And it's exactly the stiffening from homotopy, which we know is extremely weak, to homeomorphism that leads to some incredible and strange behavior if you accept the result. Okay, so let me continue. There. Okay. So I'll talk about the implication. Well, how do you prove that? Well, okay, you have to get some sense. I'm not going to go into the proof because it's seriously flawed. But essentially, the proof involves an infinite construction, infinite handle construction. So the idea is that you look for a disk that does what you want to do. So you have a disk and it's got a self-intersection, you want to get rid of it, you attach another disk. Oh no, it might have a self-intersection. Okay, let's do another one. Oh no, that might have a self-intersection, and you just keep on going, right? But you do it in a geometrically controlled way, and you hope that you can push the problem out to infinity. this is the kind of argument that, of course, is common in algebraic topology. You can do this kind of thing, but the cost is you generally can only get the homotopy. The best you're going to get when you do that kind of stuff is homotopy. And that's exactly what Castle got. The claim is that somehow by doing this, you end up with homeomorphism. How does the homeomorphism come about? Well, you have this infinite handle construction. You have an area in geometric topology where you use what's called bin shrinking. And then the final element is once you have this, you have approximation by homomorphism. Approximation by homomorphism. ADH they call it. And that's kind of just, they're the main words. You can go and look at the paper yourself maybe too. However, the problem is that this proof has never been simplified. There's a lot of, in fact, there are so many problems with this proof. The original proof that appeared in JDG in 82 is so flawed, no one looks at it anymore. So the original paper, so this is from the 82 paper, you're wasting your time. After that, there was subsequent attempts to try and come out with some kind of definitive group, where there was a book that was brought out by Freedman and Quinn. Read it again, this is in the 90s, I think that was. Again, one of the issues is they never settled on a technique. So first of all, I talked here about Castle handles. Within a year, the Castle handles had been changed. And instead of Castle handles, you had copes. And then when you didn't, in another publication it came out as capped ropes. So what are these? Well, instead of putting disks in, you put in surfaces with higher genus, and so then all this layer of complexity was put on the proof. And the idea was that somehow it makes it simpler to prove even more than the Poincare conjecture, even more than the simply connected classification of four manifolds. You could deal with the non-simply connected case. In any event, the most recent attempt introduces yet another, even more complicated infinite construction. And if you look, I mean, some of it's very dangerous. You know, infinite arguments are always a little bit dangerous. And what you find is, in the original paper, for example, when things don't work out, you throw in another infinite argument. You know, so you end up in a very, very, let's say, precarious position with regard to the overall argument of the paper. There's also a common problem in topology. There's also way too much proof by analogy. You know, so you can't even say it's wrong. It's just, I don't know if the analogy is right or not. You know, there's way too much proof by analogy in it. The other thing you have to remember is this is a very subtle problem, right? You know, when I think about this, there's nothing wrong with being wrong. If you look at all the names in topology who've worked on Poincare made a mistake when he made up the conjecture. He said every homology three-sphere should be a three-sphere. Then he found a counterexample, and they're now called Poincare homology spheres, right? Or Whitehead, you know, all the great names. These are difficult problems, and it's very easy to be fooled by what you expect to be true. Right? So we have plenty of really great mathematicians. You can very easily get led astray by this level of topology. The problems are very subtle, right? So I guess that the issues are very subtle. I mean, for example, in all of these constructions, if at any stage you end up with a manifold which has a collared boundary, so you made some assumption that gave you a collaring on the boundary of this thing, forget it, you've just destroyed all the properties you're looking for. Right? So something very, very simple can completely destroy the argument. So hidden assumptions can creep in, etc. At the end of the day, there is no complete proof of this result in the literature. There is none. There simply is none. And worse than that, actually, okay, you could say, well, that doesn't mean it's not right. The other thing is no one understands why it is true. And the final thing that we'd have to say about why this simply can't be true is we have now 30 years of hindsight. We can look back. This is the 80s. A lot of mathematics has been created since then. We can look back and we can see, okay, these were great mathematicians back then, etc., but they weren't good enough to know what mathematics was going to be like in 30 years' time. And we have more at our disposal now as mathematicians than they certainly would have. So at this point, I'm going to talk about where does this lead? What if it wasn't true, and how could you disprove it? Right? So again, I'm constructive. I'm not interested in running down anyone's theorem. I want to know what the truth is, and I want to come up with constructive ways in which we can try and get at the truth. Okay, so let me note two things. Let me start with just what happens if it is true. Right? So this is what's the standard understanding of four-manifold topology. So So the results from this theorem. I'll just call it TT just to save time. This theorem. And again, I'm just focusing in on that one specific result because everything hinges on this one result. This one result, everything stands or falls based on this one result. Okay, so what about results from the, well, it leads to all kinds of strange stuff. First of all, it leads to a complete classification of all topological, of simply connected topological homomorphic. I mean, that's an astonishing achievement. That can even be done. That can even be done is amazing. So it not just the Poincare conjecture, that's just one tiny little corner of it. It actually classifies all simply connected four manifolds by their intersection form. And the intersection form is a homological. I mean, it's a homological variant. Okay, as you can see, because there's homological conditions went into this, so that's what you're going to use. So homological. So homological data. So that immediately is very, very strong. To be able to, I mean, it's way, way, way beyond, I mean, even in 3 dimensions, you know, I guess if you drop simply connected. I mean, the problem is that our notion of classification, I should also point out, has to change when you go up in dimension. There's simply no way that you can classify 4 manifolds in the same way as you can classify 3 manifolds, closed or any simply connected even. Simply because, you know, if you drop simply connected, simply connected, is that right? Yeah, just to make sure. If you drop simply connected here, you can forget it. Every, you know, free group is the fundamental group of a closed smooth four manifold. So you have the word problem and every kind of thing once you drop simply connected. But in any event, even with the restriction of simply connected, that is still an astonishing result. What made it even more astonishing was that 1 year later, by methods of gauge theory, Simon Donaldson showed that none of this works in the smooth category. Right? So this was, in fact, I would argue that had Donaldson come out a year before Freedman, that paper would never been accepted. There's a kind of weird historical accident where it wasn't known what the situation was on the smooth side and the weird contradictions it was going to pose when this was done. So, according to Donaldson in 1983, this all fails in the smooth category. So now we have exoticness suddenly appearing in four manifold theory in the smooth category. Okay, so then you have loads of these four manifolds that don't have smooth structures. You have exotic differentiable structures and all kinds of very bizarre things. In fact, what has been found, and this is what I say that if you look back over the last 30 years, is that you have a proliferation. I mean, when I say proliferation, the field has gotten more and more confused in the last 30 years because of the proliferation of these exotic structures. And what's weird is, of course, they're not at all like exotic structures in dimension 7 and above. In dimension 7 and above, there are a finite number. We know. Here, no, forget it. Uncountably many. So you have manifolds which have uncountably many differentiable structures. Exotic. In fact, not only that, but we have them on R4. So I mean, this is just some of the headlines and stuff, but it goes. Even contractible R4 has an infinite number or uncountably many exotic differentiable structures. Right? Now, this is not true in any dimension except 4. It's unique in dimension 5 and 6 and 7. It's dimension U in 2, 3. It only happens, and it only happens because of the disk theorem. Okay? And so what you find, I mean, again, I could continue. There's all kinds of bizarre stuff. Everywhere that this result touches upon another field, it creates a dichotomy. So you have this smooth versus exotic structure, or sorry, exotic versus fake structures. You also have whether something is a knot, where it meets knot theory, it gives you these knots that are topologically sliced, but not smoothly sliced. It meets the H-cobordism theorem, and it gives you these spaces, these exotic differential structures, you know, of one type. It meets something else, it gives you an exotic differential structure of a different type, and everywhere there doesn't seem to be any relationship between any of them, except they happen to contradict this theorem. Right? So every single exotic structure that's discussed in R4 is because this theorem contradicts something that comes from the smooth side. Every single one. So what you find is that, and again you look back over 30 years, you realise the field has gotten more and more confused. There doesn't seem to even be relationships between these different types of exotic structures. You know, everywhere that this result touches anything else, suddenly we have this new weird behaviour. Okay, so I guess I got interested in this question back in 2010, 2011, I suppose. I started really looking at it. And I was really interested in smooth 4 Poincare conjecture, dimensional Poincare conjecture, and I had the question that for the start of this talk. And as I started studying it, I began to be concerned that this theorem was not, it was not understood. All this stuff really didn't, the proof wasn't there. And I'd say, okay, well, I got to try and air these with the experts. I mean, I'm not a topologist, I'm a geometer. I work in topology as well. I certainly have been immersed in topology for all of my career. So I put up a series of MathOverflow questions in which I tried to probe the various aspects of this problem. So the MathOverflow questions that I put up, I mean, initially they got edited very heavily because I was suggesting that Freedman was wrong, etc., etc. This theorem may not be correct. But anyway, I still kind of persevered and tried to give it in a way that allowed it to be kind of, well, at least non-confrontational. So the first question I asked, and I'll come back, the first question I asked was, is there any other evidence to support this theory? Now this is 30 years after it's 30 years after this result. Is there any other evidence to suggest, so that might give us new techniques or new ideas that we could use to try and see why this is true if it is indeed true? The answer after thousands of views and quite a bit of conversation is no. It's a single result. There's no other evidence that the classification of simply connected topological form manifold should be as simple as there. In fact, all the evidence is that it shouldn't be. All the evidence is the opposite. The next question, I said, well, okay, let's look at this issue of fakeness. These exotic form manifolds, could they be fake? Maybe this dichotomy between homotopy and homeomorphism is what we're looking at, not between homeomorphism and diffeomorphism. Right? So maybe that's something's not right in that regard. So the second question was, is all exotic form manifold behavior down to this here, down to this here. And here the answer is yes, that there is no other construction, there is no other indication anywhere that exotic structures come except from this theorem, in 4 dimensions. But I could point out, going back up here, what other weird things, like if you take any form manifold, compact form manifold, you puncture it, take one point out, it now has an uncountable number of differential structures on it. It's a kind of preposterous statement in some ways if you were just to step back and know nothing about the field. How could that be? And certainly it doesn't hold up with anything in higher dimensions. So again, is all exotic form manifold behavior down to, and the answer is yes. Yes, no, again, these are all the experts in the field of MathOverflow, we're all happy to throw in and but essentially, all exotic behavior appears to be because of the dichotomies created by this theorem. Okay, so let me now kind of move a little bit towards how can we resolve this? What possible steps could we take to try and understand what's going on here? What kind of candidates? I mean, in mathematics, we have something of a naive view of our profession, and we believe mathematics trumps politics. But sometimes that's not the case. But mathematics never trumps social interaction. And so when something gets established, it can be quite hard to get rid of it, even though it might be completely preposterous. So unfortunately, my contention is that that's precisely the situation with regard to the disk theorem. Okay, so let me say, let's put that aside. Let's say, what do we believe, or what could be true? Well, the first thing is, and I'm going to go back to what I talked about homotopy equivalence. Homotopy equivalence is very, very weak. There are lots of bizarre things in homotopy equivalence. So I just gave one example, but of course there are a lot more. So let me just point out the following here. So these are classical, and you know, mathematics has a habit of forgetting and then reminding itself of, you know, so all these come from the 50s and the 30s and the 60s, you know, from a long time ago. So for example, there exists uncountably many fake ORMs for n greater than or equal to 3. There are uncountably many fake ORMs. These are contractible four manifolds. They have exactly the homotopy type of ORM, but they're not homeomorphic to ORM. And this is true from dimension 3. In fact, when you look at homotopy, it's one of those things, lots of nice things happen in 2 dimensions, but once you go to 3, forget it. You know, once you go to 3, homotopy gets worse. The higher the dimension, the more you can mess around with the boundaries of objects. You have more ways of combining them. So, for example, the Jordan curve theorem works in the plane, simply connected, it bounds a disk, you're done, right? Not true in 3 dimensions. Alexander Horn sphere, that immediately said you can't do that, right? So, once you go up in dimension, homotopy takes over. Once you get to dimension 3, homotopy can do crazy things to your, and still make it look like it's okay, right? So these are all distinct homeomorphisms, right? These are all distinct, but they have the same homotopy type. So then you say, well, hang on. Are we now saying that just in dimension 4, these uncountably many fake R4s have uncountably many differentiable structures on them, and just in dimension 4? It doesn't sound quite right. It sounds like a case of mislabeling it. Because, you know, you could ask the question, well, surely there's counterexamples. Yeah, there's lots of counterexamples. They're just all mislabeled. They're all fake, but in fact they're claiming to be exotic. And let me show you how these things get better in dimension, or get worse in dimension. You can do more and more crazy things in dimension, various dimensions. So let me just give you one simple example and show you just how easy it is to make a fake object in higher dimensions. So if the classic example is Whitehead. So Whitehead constructed a fake R3 in 1937. So it's called the Whitehead manifold. How do you do it? Well, you take a torus. I'll just go on like that. That's a T0. And inside this torus, we draw another torus. Now, all we draw is a curve, but it's what's called a Whitehead link. So it's just a double and you kind of clasp it. Right? Okay, and so they call that T1. And then what you want to do is take that torus and you want to replicate a doubling inside. This is called a doubling. So in other words, you take that one and you put another one with a little clasp, and you put, you know, so you get a sequence of tori. Tori 1, and then inside it you've got tori 2, and then inside you got, etc. And each time you're doubling, you know, you're doing this doubling with clasp, doubling with clasp, doubling with clasp. And if you
the 2 torus?
2 torus, yes, solid 2 torus, and then I've just drawn it as a circle, but think of it as a torus, and then you can put another little copy of the same thing clasped around inside. So you have to double each one of these strands and put a clasp in it, right? And then do that and iterate that process. And if you take S3, I'm assuming that's just all in S3, and you take out the infinite intersection. This infinite intersection is a continuum. It doesn't look good. It's called the Whitehead continuum, and it looks kind of like a counter set. And what you get is this is a fake R3. It turns out that this R3, that this is contractible. It has, so you have to do a bit of basic topology, a bit of algebraic topology, you can show that's contractible. By the way, Whitehead claimed that this didn't exist first, and then he found it, and then published it, right? So again, nothing wrong with being wrong, but you have to recognize when you're wrong, and you've got to correct it, and that's exactly what you have in this case. So that's one example of a fake R3. You can now, Macmillan in 61, constructed uncountably many. Now what I think is interesting about these papers, how do you tell that they're not homeomorphic? All of the usual ways we have of telling whether the two things are the same are kind of like the fundamental group, or they're homotopy invariants. We want something finer. We need something that actually, picks a homeomorphism class, right? So you need invariants of homeomorphism type, and that's what we use. So they construct in homeomorphism invariants. That's very important. They're very hard to find. Most everything we have is homotopy invariant, and that's not what we're trying to get at. We're trying to distinguish between different homeomorphism types. So this was a famous example from the 30s that showed you, well, you could have things that were contractible. How did he show that this was not the same? Well, you could show that it's not simply connected at infinity. You had some specific, thing that could tell you that this was not homeomorphic to R3. But when you go to dimension 4, it's even easier. It's even easier. You can make compact bodies that have boundary that look like the 4-ball. So here, this is the famous example again, Maser in the 60s. Okay, so here, I'm going to just try something. So what I want you to think of, you're looking at S3. So you're looking at S3 here, and it's the boundary of 4. So behind the blackboard is the rest of the 4-dimensional space. And what I'm going to do is take the circle, and what you do is you take the circle, and you think of a disk sitting in this 3 dimensions, and you push it into the 4-manifold behind. And then you remove that disk and a normal neighborhood. It's like cutting a hole right through the disk, right through the 4-manifold. So this is what's called, it's a one-handle, in fact, is the way to do it. So again, it's removing normal neighborhood of the disk, the obvious disk that bounds this, pushed into the 4-manifold.
Sorry, I'm just a bit confused. So how do you want to do this? So you have S3 and then...
And S1 sitting in S3.
S1 sitting in S3.
And think of it just a standard disk.
In S3, like...
In S3,
okay.
and then push it into the 4-ball. Change it by color, however you want to view the 4th dimension, right?
Yeah.
Now remove that disk.
Okay.
Cut it out, it's a set. You can just remove a normal neighborhood. This normal neighborhood will intersect this in a flattened torus surrounding this circle. Right? And so when you do that, you generate an element of pi1. It's a way of attaching a one-handle. Okay. Now, the other thing you can do, a lot of 4-manifold topologies of this torus is called Kirby calculus, where you kind of picture what you're doing to the 4-manifold. So here I've cut out this normal neighborhood of a disk, but you can also attach a handle. Now, if you attach a handle, what do I mean? I mean, I take this circle, say this one here, over here, and I think of a disk attached to this one, and again, I'm taking it. But this is outside of the manifold, I'm gluing that on. So I've dug a hole out, and I've glued something in. Okay, now if you do that exactly correctly, with a certain framing, there's a certain framing because you could kind of twist these corners in some sense, this is the same as before. These two cancel. So this is like digging a hole and filling it in. That's the analogy of what's happening here. Right? So that's really a 4-ball with that. You dug it out, and then you filled it in, and you still have the 4-ball. Okay, so that's just, all right, so Maser's manifold is you do more or less the same kind of thing. Because it goes under, I think, properly. Here's your one with the hole on it, and that's the dead side, that's that side, and there. So now I have, here's the hole, but instead of going around, I just went around kind of one extra time, and I put a clasp in. Okay? No, just same kind of thing. This is a 4-manifold. It has boundary. It consists of, you've kind of cut out, you have a one handle that you're after kind of creating by this, and you've attached a 2 handle. So you can give it a cell decomposition, you can write it down very explicitly, and its boundary is not simply connected. Homotopy can undo clasps. So this is the thing, the difference between homeomorphism and homotopy. Homotopy, you're allowed, like if you take a knot in R3, you can always homotope it to the unknot, because you can just cross it through itself. You don't insist that everything be embeddings or anything. Same thing here. You can undo this clasp. If you undo this clasp by homotopy, you get this, and you get B4. So this has the same homotopy type as B4. This is a fake 4. Okay? Very easy to construct it. That's just one. You can construct fake objects, like, you know, with this, generalizing this construction, going through it a few times, twist it around. The thing is always to show that what you get is not just a standard four-ball. Usually you show this is not a standard four-ball by showing that the boundary of this manifold is not, it's not simply connected. It's not, right? So the boundary of this four-dimensional object. So again, I've taken an S3, I've cut the disk out, and I've glued something onto it. It's a very simple construction, and immediately you can find these weird things that have exactly the homotopy type that you want without actually being
What have you
homomorphic.
moved on there? Sorry, that I got confused. I understood the first picture, but what's going on in
This one?
Yeah.
So, homotope this. Okay, so you're allowed to do a homotopy just to move it around by,
Yeah, but what is this class thing? So is that a torus? Or
So again, it's a two disc, so it's a handle, it's a D2 cross D2 attached along one of the boundaries, which is a boundary is an S1 cross D2, and you attach the boundary.
Okay.
Yeah, so it's a circle, and it's a regular neighborhood, and you're gluing on then onto this, and up with a fattened disc.
But you attached it in a different way.
Yes, so for this one, I dug a hole out inside the manifold, and for this one, I'm kind of attaching it from the outside. Right, so
So
the
it has a clasp which that one didn't have.
This one didn't have. So, but homotopy undoes clasps. You can homotope this without changing homotopy type, in which case it reduces to this, and as I claimed before, now frame should be 0. Okay, what I want to point out, you don't have to go through infinite constructions. You don't have to go through continuums. You don't have to go through any of the more complicated stuff in 3 dimensions. Once you get into 4 dimensions, now you can start making very, very simple fake objects, things that look like one thing at a homotopy level, but are homomorphically quite different. And they're everywhere. They're absolutely everywhere. There's uncountably many of them. You have them for Rn. And it starts in dimension 3. There's nothing special to dimension 4 about this. It starts in dimension 3. But it just gets worse the higher the dimension. Okay, so again, what I want to point out is that these manifolds, this is the 4-dimensional case or the 3-dimensional case, you can construct fake objects very simply. Homotopy invariance is extremely weak. And again, it makes it all the more surprising how the disk theorem can claim that you go from homotopy to homomorphism. Right? So again, these are so easy to construct. Okay, so the third question I asked on MathOverflow, and I'll leave you with this, is was an attempt to try and see, okay, so there's no support for this result. It's completely isolated. It has no other supporting evidence to suggest that it's true. And not only that, but at least all these bizarre things. And every single exotic form manifold is in fact a consequence of this result. And the third question I put up to say, okay, well, how can you disprove it? How are we going to disprove it? So for the third question, what I asked for is, how many dichotomies can we find created by this theorem? So these strange dichotomies between smooth and homomorphism, between homotopy, homeomorphism, and diffeomorphism, if we can find exactly where these touch other things, maybe some other methods from a different area can lead to a contradiction and show you this simply can't be. Okay, so with that, from question 3, I came up with a number of different ways in which it could be gotten rid of. So this was for question 3, how to disprove it. Find out where all the contradictions are. Okay, so again, it's a rather difficult thing because it keeps creating these dichotomies. So every time you have a counterexample, it gets mislabeled. So it's not, that's my argument. That's why it's not that these counterexamples aren't there. They're just staring in the face, but they're just being called exotic. So we have to show, okay, well, how would you show that they're not exotic? They're in fact fake. So the first method would be to find new homomorphism invariants. That's what has to be. That can distinguish between these cases that are supposed to be homomorphic. Right? So new homomorphism invariant. And as I said, there's a certain element that has been forgotten in the 60s literature in which these kind of things were pursued in 3 dimensions and higher dimensions as well. So these could be, the various types that you could have for that, but I'll just leave that open, I guess, for the time being. Just some homomorphism invariants that would be that would disprove it. Okay. Secondly, what other way? Well, the other way we could do it, I guess, maybe not as straightforward or as direct, is to split the categories a little bit further. So for example, we have homeomorphism. and we have diffeomorphisms. But, you know, so we're kind of concerned about whether these two match. I mean, as far as I'm concerned, in fact, I would say in dimension 4, once you have homomorphism, you have diffeomorphism. Right? That the distinction is almost zero between the two. But how would you get from here to here? One way to do it would be to take, so for example, this is a paper by Donaldson and Sullivan. And what they showed is that the diffeomorphism thing works even if you assume something weaker. In fact, by Lipschitz is what they... so you don't want the maps quite the diffeomorphisms, but you want them a little bit more than homeomorphisms. And they showed, well, that's enough. You can define these diffeomorphism invariants, modular space or space of connections, in this slightly weaker, by defining a weaker set of differential equations, etc. Now, there's an attempt, so this is definitely going in this direction. They showed that essentially this and diffeomorph is pushing in on this homeomorphism. I want to completely erase this distinction. So you could also imagine, instead of using by Lipschitz, you could use Holder, you could use some other space that's slightly, you know, more refined, but nice space. You could, so again, maybe here and here. One little piece of that has been done, but again, that's one way to do it. Would be to refine still further the categories that are there. And the other thing, I guess, which is an interesting area and has kind of proceeded independently on its own parallel track, and it may be time for it to come back into the mainstream, is to look at open manifolds, and in particular relative homotopy invariants. So, as I said, the way that you show, for example, the Whitehead manifold is not R3, is show it's not simply connected at infinity. Right? This is one way of describing it. So, relative homotopy invariants, and in particular, like fundamental group at infinity for these infinite constructions. For again, most of them are just these infinite constructions with, you know, the add an infinite number. And by the way, if you have a contractible n-manifold, it is exactly homeomorphic to Rn if it's simply connected at infinity, except in dimension 4. Right, so again, it's another one, almost every theorem you state between these two categories, you always have to say, except in dimension 4, right, because of this disk theorem, right, that's the... Okay, so at that point, I think I'll say thank you for your attention, and I'll take any questions.
Any questions?
Why in this theorem do you embed two-dimensional disks into 4 manifolds? Could you do that into more dimensional manifolds?
Yeah, but they're going to generic disk in a 5 manifold is embedded.
Oh, so only in lesser dimension. Oh, right, there is a theorem for that. Sorry.
You get that? No, it's important. I mean, there's a kind of a you know, for everything stranger in 4 dimensions. Well, yes and no, it is true. The main problem is that these disks, if you look for an embedded disk, the best you can get is an immersed disk, right? So one that may have self-intersections. And then, how do you deal with self-intersections? And again, why are you interested in disks? Because you want to use the fact that you have simply connected or blah, blah, right, at some point. So how do you do that? Well, if you have a disk, you can contract your loop, right? So that's a way of kind of simplifying things when you have these nice disks, because then you can contract and you can end up, you know, simplifying the manifold in that way. But the problem in 4 dimension, in 5 and higher, that's great. You take a generic disk and it's embedded. If it isn't, you can just push it into one of the higher dimensions, you know. But in 4 dimensions, 2 plus 2 is 4. So you're going to have a 0-dimensional intersection, which is generically points. Some might be plus, some might be minus. They may add up to 0, but you may not be able to get rid of them, right? And that's the issue in dimension 4.
When you want to do squashing and stuff like that,
Mm-hmm.
okay, you can do that with 2-dimensional disk.
Mm-hmm.
You can also do that with 3-dimensional disk. And you could then encounter the same thing, because, well, if you take 3-dimensional disk
Absolutely.
and try putting it to R5, for example.
Absolutely. But that's okay. But if you want to come up with conjectures about pi2 of a 5 manifold, these are the questions you'll have to address.
Oh, okay.
Well, when you're talking,
I was just trying to ask people tried to prove other versions of this theorem.
Oh, yeah.
To create contradictions, because for
Yes.
higher dimensions, you know.
It could well be. I agree. It's a good point. The problem is that it's so special to this dimension, the whole machinery that's been brought out. In fact, my own personal criticism would be that it's a little bit of a naive interpretation of three-dimensional stuff in 4 dimensions that I think is inadequate. And the geometric control is not sufficient in 4. If you go to a 5 and higher, it's going to be even less useful. It's going to be, there's no way it's going to control it. But it is true, yeah, of course. But we always like it to look at simply connected. And once you talk about simply connected, you're contracting loops. And once you're contracting loops, you're talking about 2-dimensional disks. That's the reason why 2-dimensional disks have a particular role in the questions we ask. But if you ask questions...
Basically, we should then switch our question from what happens if we set fundamental group
Yes.
to be certain, chosen by us to choose a higher dimensional homotopy group.
Yeah, absolutely, and people do. All people do. I mean, obviously, the higher manifold theory, they go on and continue. But what is probably true is that things get crazier and crazier the higher the dimension. You have to impose more and more to really get control. Because there's so much different ways. You won't get classification.
I was just asking because, well, if this theorem looks so strange in 4 dimensions, because, well, we use 2-dimensional things and we cannot embed them, then maybe if we take, well, there's an obvious notion, that's why I'm asking, if we take higher dimensional object that cannot be embedded, maybe it will provide some
insights. The other thing I think is also quite interesting is that most of these homotopy things disappear as soon as you cross it with OR. So if you take the Whitehead manifold and you cross it with OR, it's homeomorphic to OR4. Right? So once you just cross with OR, it's the simplest possible way. All the kind of homotopy craziness disappears, right? All the possibilities disappear. So, but then each new dimension has its own new brand of craziness that comes in, right? Then you have even more ways to, but lower dimensional ones tend to trivialize once you cross them with OR. So yeah, there are relations between dimensions, but it's not always that something complicated. It's like undoing knots in higher dimensions, you know what I mean? It's that kind of thing. So.
Any other questions? So we thank the speaker again.